Welcome back, everyone. I'm back again with another coding video. I know everyone really enjoyed the text rendering optimization video, so I thought we'd write some code again together. This time we're going to take a look at optimizing blur effects in OpenGL. Uh, I really appreciate all the positive feedback you gave me on that video. In terms of the game, I'll just mention here, I've got Update 2 coming. I know I made the video. Very soon I'll be done with testing and it'll be out. Just give me a little bit of time and we'll get there. With all that preamble said, yeah, we're going to hop into it. We're going to start writing some code and we're going to see if we can learn a little bit more about blurs in 3D graphics and how we can do them efficiently. So a little bit similar to our text rendering optimization where we're going to try and do things as efficiently as possible, but a little bit different in that we're not going to just start with the Learn OpenGL starting point. We're going to make some code together and from there grow it and try and learn about some different things. Okay, so a couple things to mention before we get into this. I'm trying to get to the point quick. First off, just like the last time, I'm going to provide the code on GitHub. Both I'll provide my starting solution and my ending solution. Maybe I'll do the steps in between, I haven't decided yet. You might notice there are some differences between what you see in the video and the code I provide. That's just, it's really hard to get code in the perfect state before you make a video, so there might be some modifications. And I'll try and call out as we're writing code areas you might want to do things differently if you're working on a bigger project. This is all one file I'm going to be using, one CPP file, so everything is a bit rough, it's a bit messy. So as we go through, I'll try and tell you with the code things you might want to do differently. The other thing I'll mention here before we get going is I need to give a big thank you and a big note to Learn OpenGL once again. Their Bloom tutorial is a great starting place for learning about blurs. We're going to cover a lot of the content in here, and we use this as a big basis for this video. And the other kind of tutorial that I'm going to call out here is Intel has this really great, I guess, tutorial guide article about efficient blur algorithms, and it's really awesome. I'd highly recommend you check this out after you finish the video if you want to learn more. We're going to use a lot of what they talk about in here, and they also provide a really nice project that you can run on your computer and you can try out some of the different blur algorithms with. With all that said, I think we can finally jump in. Sorry for the slow start. And so let's start talking about blurs. So I know I'm saying this like it's very obvious, but the first thing we need to talk about is why do we need blurs? Why are blurs used in 3D graphics? So we have some examples here with this Intel article that are immediately two good examples. Blurs are used to blur an image. Just like if you open up Photoshop and you apply a blur, Photoshop has lots of different options. It'll blur the image you have on screen. So with Learn OpenGL, this first comes up when we talk about bloom. And the idea of bloom is if we have very bright areas of our scene that are exceptionally bright, we can blur that brightness, like here, to make it seem as if it's kind of overwhelming our view. We can also do this with emissions. So if an object is supposed to be glowing, it's supposed to emit light, oftentimes we'll blur those colors to try and give it that faked appearance of emitting light. Kind of gets into a different direction once we start talking about lighting. You can have objects that actually cast light and also use a blur to make the object itself look like it's glowing, or some games will just fake it. It won't actually cast light, so in this case this box is lit. It wouldn't be lit blue. We just do this glow around to try and kind of simulate that view. So that's one example. Another good example is depth of field. So this has become pretty popular in the last, I don't know, 10 years. I feel like there was this real turning point with like the Xbox 360 that time when depth of field came around. This is to try and emulate cameras better, real world cameras. And the idea here is when you render your scene, you try and decide this is the depth which is in focus with our camera. Everything that is closer or further away than that depth will blur. And so we selectively blur images in our scene. As well, I'll just kind of mention it's a really good tool you want to have in your pocket as a graphics developer, blurs, especially just for anytime you have results which are kind of pixelated. Depending on what it is, you can apply a fast blur to it, and instead of being noticeably pixelated, it'll smooth things out. So sometimes for me, I've used them for shadows when they come up, and then also even like highlighting objects, I've used them as well to have a little bit of a glow and to remove that hard pixel edge. Okay, so with that kind of long spiel about blurs done, let's start taking a look at some actual code. So what I've done here with this starting point is I've gone into Learn OpenGL starting solution, just like we used last time. But this time I've taken their starting point and I've modified it a little bit. So I've used their texture example and I've modified the code. The main reason why I used their project was I just didn't want to go through and include all the DLLs and lib files, and I was also a little bit concerned. I think that starting with this gives us a good jumping off point of everybody has image loading libraries. We already have GLFW included. It just kind of gives a standardized starting point rather than if I were to use my engine or if I were to start a new project. I don't know for sure that you're going to have the same stuff included. Okay, so with this starting point I've created, I'll just show you. This is just taken the textures example that was already in Learn OpenGL. We can actually go over to it. Oh, no, it's getting started. So super basic, just learning about applying a texture to a quad. It's taken that example and it's just set it up a little bit better to have multiple textures loaded and rendered on screen. So I have the crate, the box that it starts out, and if you hit 0, 1, or 2, you can change the images. So I've used this screenshot from Redeemart, and I use this matrix number code that came with Learn OpenGL. Just to provide some variety so we can test this out with some different objects. I also have this running as a console app, and I've outputted the FPS here, but it's probably way too fast to actually follow. So we'll use RenderDoc to check out the performance. Let's take a look at what I've actually done here. I'll say again, I mentioned it before, this is all in one CPP file. I was kind of torn about this because I think that there are some not great practices doing this, but I also didn't want to overwhelm people with multiple classes and creating all these things. You can really get into the weeds, so I've shoehorned everything into one CPP file. So I've created a class called texture data. So this is just to hold on to a texture. So it has a string, which is the file path, so where that texture is located. It has a unsigned int. I like to use this GL unsigned int. I know with Learn OpenGL, oftentimes they will use just a unsigned C++ int. I just use this just because I believe that's what you're supposed to use. I also have GLM's vector2 for the size, so the X and the Y resolution of the image, and I have an int with the number of channels. So is it RGB, so 3 channels, or is it RGBA for 4 channels? And I have this constructor which will take in a path and save that to the file path. This functionally does very little. It's just a wrapper to try and make things a little bit cleaner. Underneath this, I have some loose global variables, which I would strongly not recommend. Oh, I guess I'll also mention, I like to do m underscore for member variables, just a style thing. So I have one variable for the texture number, which is just holding on to which index in our array or our vector are we rendering at any given time. So when you hit a number key down in process input, if you hit the 0 key, we set texture num to 0. If you hit 1, we set it to 1. So this is just to access the array at the location you want. And I have this vector of texture data. This could have been an array. I just like using vectors instead. So if you don't know, in C++, a vector is a dynamic array. It works just like a normal array, but you can add and remove, and it'll resize on the fly. It is a terrible name. If you've just hearing this now and you're thinking, why would you name a data class or a data structure that? It's a bad name. So I have a vector of texture datas, and I've just set them up with some paths here. So I have that container that we use in the default example, I have that matrix, and I've added in a screenshot from my code, which is just that Redeemart screenshot. I also changed the width and the height resolutions here to up them. When we get into performance, especially with graphics, oftentimes you kind of have to run at higher resolutions to see differences. This could really be bumped up to 1920 by 1080. I just kept it as this so we can see the background as well, and if we want to run two simultaneously, we could compare. I don't think I'll actually do that, but okay, moving on. So I have load textures here. So this is obviously a function that'll go through and load all of our textures. This is really taking what was in textures.cpp and it was written out once and just adding it to a function. All of this is kind of a mess because I have these global variables. You're not passing anything in. But we loop through. I'm using C++ range-based loops. So we use this for, if you're unfamiliar with this, this is the same thing as just making a temporary variable called text, which is a texture data, and saying for int I is equal to 0, I less than textures.size, I plus plus, and then before doing anything saying text is equal to textures at I. Okay, so that's more on the C++ side. This should theoretically be a little bit faster doing this. So we go through, we get that handle variable which we've created, which is going to hold on to the reference to our texture we make on our GPU. So we generate that texture, we then bind it. We set some of the wrapping parameters and filtering. You can obviously go through and set these however you'd like. And then I'm using that STBI load. I don't actually use this in my engine. I use Devil. It's a different image loading library, but this is quite common with OpenGL. Excuse me, we give it the path to our file. I use these width and height variables. The only reason why I created these instead of using our size here is because size is actually two floats, a x float and a y float, where this function is looking for 2 ints. So we do this, and then after we get those values, we set the size with it anyway, and we pass the number of channels here as well. So this should theoretically load our image if everything is good. We set the size for our texture to the width and the height, and if the number of channels is 3, we generate an image which is just RGB. If it's 4, we do RGBA. And we use this to create our image, and we pass in the data. So now our texture here on the OpenGL side, on the GPU side, should have that texture be ready to run. And we generate a bitmap. That's not quite as, I don't think it'll be necessary in this, but it's a good practice. Have our cout if there's any issues, and after we're done here, we have our image library saying free this data. So this is allocating this data on the GPU. Once we have that allocated on the GPU, because we're not going to do anything else with that image, we can remove it from RAM. We don't need it on our CPU side anymore, so we free it. Okay. Most of the other stuff in here, if you've done Learn OpenGL, this is kind of the standard practice. We'll go through just so everyone feels comfortable, but we set up GLFW. This is set for 3.3. It's always great anytime you can make a tutorial that runs on earlier versions of OpenGL just to maintain compatibility for everyone. But you could totally switch this to 4.6, the most recent version of OpenGL. Maybe you'd have a little bit of performance gains, I don't know. Or if you just want to be on the cutting edge, right? The decade-old cutting edge. We have our hints for if it's Apple or not. And then we have GLFW create a window. We set it up. If it's equal to null, something has happened. We set the current context to that window. We set that frame buffer size callback. Our code really isn't set up to adapt to this, but this will just change the view buffer, or the viewport rather, if we adjust the size of our window. But all just good practices. And then from there, we start loading our shaders. So we have our texture, vertex shader, and fragment shader. Pull up over here. I've done some modifying in here with the data. So before, I think that there was color as well being set. I just pulled those out because we're not actually using those. So all that really happens here is you have the position and you have your coordinates. in our vertex shader, they get passed along to our fragment shader. Visual Studio doesn't seem to like the fragment shader, and we sample a texture and return it. So this is super, super simple. Really, this is just trying to draw these textures on screen. Very little happening. I think I adjusted some of the values in here, our vertex data for the order and our indices. But I'm not too focused on this information or this setup. There's probably a little bit of tweaking that could be done here. I'm not sure if it uses a triangle strip or triangle points, but either way. So then we load our textures. I have this set up with the frames per second, so I use GLFW to get the current time. I set the past time to that, and then so every time we just update, I'm kind of moving these along. So I set the past time equal to the time, and then I say time is equal to GLFW get time. So this is going to be the delta every single time we update, and I see out it, and I use that return character. So instead of doing a whole bunch of new lines in our console, we just keep rewriting it. We'll see if we can actually use that. I think that it's just too squirrely. It updates too quickly to actually be of use, but that was kind of my idea there. I think everything else here is just about the same as it was before. We clear our window, we bind our texture. I think I probably should be activating our texture 1 here. Just double check. Yeah, so it's clearly working. This isn't a problem, but I'm just going to activate that texture. GL texture 0, just for good practice. But okay, so we render our texture on screen. We bind that, use our shader, bind the VAO, vertex attribute object, and we draw our elements. I guess something else I'll add in here while we're at it. Right now, this isn't going to accomplish anything because the viewport's already been set properly, but we might do some messing around with the viewport. So I'm just going to make sure before we go to draw, we always set it to the size of our image. Okay. So we swap that front buffer and the back buffer, display it on screen, pull our events. That's about it. And then the other thing I'll call attention to is we check to see if someone presses the escape key or if you hit the stop button in Visual Studio. That means our window should close and we'll exit and hopefully clean everything up. I don't think I even free the textures on the GPU. That would probably be a good idea, but that's fine. I'm being lazy about it. Okay, so that's our starting point. Everything looks good. We are now going to work on getting some blurs in. So the goal here is we're going to leave everything in place here. We're going to modify very little of what we actually have now, but we're going to add in, before we draw, we do our current render call, we'll add in one more step which will potentially blend our, or blur our image that we have selected. So we'll have it optional so we can toggle it on and off, and we'll do some keyboard handling. So if you press, I don't know, we'll do like the B key. If you press the B key, then that means blur the texture, and we'll run that shader. Otherwise, we'll just draw it normally. Okay. So let's start to, where should we jump in next? Maybe before we do anything else, we'll start talking about how we actually accomplish blurs. All right. So there's actually different ways you can do blurs. Oftentimes when people just say blur, especially in game dev or in graphics, we're talking about what's called a Gaussian blur. Without getting too deep in the weeds, I want to make this pretty accessible. The idea here is we have what's called a kernel or a matrix, which is some weights, and each pixel in our image, we will go through and we will apply those weights to that pixel and the surrounding pixels to try and almost average out the image. So we can see this better in the Bloom tutorial here. So a Gaussian function, it's very similar. It is a bell curve in school. So if you ever you're in university or college and you say ride that bell curve, that's what this is referring to. So the idea here is we sample textures around, or we sample pixels around the pixel we are currently looking at, and we take those values and we apply weights related to this curve to blend them all together and do a bit of blurring. So in this example here with what we're looking at, I know this kind of goes on to talk about more of the implementation, but we have this Gaussian blur. So for this one pixel, we will take all of the pixels around, multiply it by weights related to this bell curve, and we will set the value for that individual pixel. Okay, so this is actually a better little bit of image that we can use to take a look at this. So our textures are 2D. We want our blur to be applied both in the horizontal and the vertical, right? You can see here with what Intel, this article, is described as the naive implementation, we have a 2x2 grid, which is if we want to blur this pixel, we're going to look at all of these neighboring pixels around, and these are the weights that you might use. You can adjust the kernel size, which means we can grow or shrink this array, or this 2D array, I should say. And you can also adjust values, which oftentimes we use this value sigma, which will determine kind of the distribution of the bell. We don't usually worry too much about this in graphics, but if you want to learn more about this, this does come up. Okay, so quite a few different ways we can get started. Maybe we'll start with a little bit of the C++ kind of setup before we jump in. So I'm going to add a bool to blur. So this is just going to be our way to keep track if we should be blurring or not. The other thing I'm going to do is I'm going to add a bool blur pressed. This is very silly, but with GLFW, I think we can set this with sticky keys, but what you'll find is it's because you press the key, it's very easy for GLFW to set blur to true, then set it to false again, and set it to true and set it to false again. So I'm going to add another bool, which is just going to make it so when we press our blur key, we do that once and we set blur to true or false, and it's not until we release that key that we're then able to set it back again. So what does this actually look like? Scroll back down to our inputs here. I think we'll have to do a little bit of modifying in here. We'll have to expand this slightly, but so right now we set all of these. I'm not using curly braces because I'm doing all these like that. I'm going to go through and I'm going to set this up. Oops. This obviously, right now we are only running one line of code anyway here, so it doesn't actually affect anything functionally. I just always like to use the curly braces. Sorry, I'm not quite warmed up yet. Okay, so we're also going to check now to see if, I'm going to say the B key is set. If you're ever interested, I know I try to cover a lot of stuff in these videos, but if you're ever interested in different keys, what you can kind of search for, if you type GLFW key, IntelliSense will give you tons and tons of options here. And this KP here means keypad, so you can use the num keys as well. Okay, so if B is pressed, we're going to check to see if blur pressed is false. So once again, sometimes people aren't comfortable with this. This not is the equivalent of saying if blur pressed is equal to false, just doing a not in front. Make things a little bit easier, because if this is false and we invert that, then this will be true and this will pass. If it's true and we not it, then it'll be false and we won't pass. Okay. So we're going to say blur is equal to not blur. So if blur was true, it'll become false. If it was false, it'll become true. We will then say blur pressed is equal to true. Now the only way our blur pressed is going to be equal to false is if our B key has not been pressed. That's why I'm breaking this nice logic of else's. Okay, so that looks pretty good. What else do we need to do here? I think maybe we'll jump into our shader, because we do have a fair amount of work to do here. Okay, so I'm going to make some shader files. For whatever reason, with the Learn OpenGL setup, Git has made all of my files read-only, so I can't modify them. So I'm going to make it on my desktop. I might even just drag and drop some files. But you're welcome to create them here, add them to your project. I'm going to use Sublime Text, and I'm going to do it on the outside of this file setup. Okay, so maybe I'll just copy the texture shaders that I looked at, that 4.1 texture, and I'll just modify them. So I'm going to call them, maybe I'll call them Simple Blur and Simple Blur, obviously with VS and FS. Okay. So these are straight copies of what I had before. This is our texture function, which we're going to have to do a little bit of modifying with. So what's important to keep in mind is when we were rendering our texture on screen, I know we're not actually applying a matrix to that quad. We're not transforming it or anything. It's very simple. This shader is going to take place on our image. So when we apply our shader, we want to run it right across our image. Okay. So this looks good. Do we need to do any modifying? I might just change this to text coords just because it's a little bit nicer. But otherwise, that's good. So we're going to pass this through. So it's still kind of a quad shader, sometimes referred to as. Okay. So we have our output color we're going to return. That is the same. We have our text coords, which is coming in. That is the same. We have our image we're going to be sampling. And as we work on this, this code is going to be very, very similar to the Learn OpenGL code, which we'll take a look at in a bit. So we're going to pass along an array of weights. And we're also going to pass along our kernel size. Okay. So the idea here is we're going to use these weights and this kernel size to determine how large a radius to look at our image or our pixel around, and these weights are going to be the weights we use to apply to the pixels around it. I feel like I could probably spend a bit more time explaining this, but okay. So let's take a look at Learn OpenGL's code, because we're going to be using this as kind of our basis. So it's important to keep in mind Learn OpenGL, its example is all around bloom. So it's not just a blur shader. What it does is it renders a scene, it looks for bright spots in the scene, it blurs those bright spots, and then it combines them. Okay, so it's doing multiple things. So with this shader, which is quite similar to what we're going to be doing, they've gone in and done an optimization, which is super common to the point that nobody doesn't use this optimization when we do blurs, or even when we use kernels of any kind. So this is the naive implementation. The reason why it's naive is for each pixel in this image, we now have to do 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So we have to do 7 times 7, 49 samples for each of the textures around, right? Which is quite costly. And depending on the kernel size is really going to impact performance. But the really nice thing is this is actually separable. So this is what's called a convolution kernel. What we can do is we can separate it into two 1D arrays like we have here. So we have a Y and an X. They're actually the exact same values, but the idea being, instead of looking at the 2D space around our pixel, we can do one pass where we do horizontal. So we just look at all of the surrounding 7 pixels, and then we do vertical. So we do the surrounding 7 pixels vertically. And the result is, although this is two separate shader calls, instead of doing 49 comparisons for one pixel, we only have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So this is much more efficient. And this is common with any convolution kernels. So they talk about Sobel filters here. Sobels are used for edge detection oftentimes. And there's a whole kind of area of academia around this. So we're going to do something very similar. And this is what Learn OpenGL does as well. They blur horizontally, then they blur vertically to create the same effect. Okay. So in order to achieve this, just like Learn OpenGL did with its example, we are going to add in a bool. Okay, so depending on if horizontal is true or not, we will sample horizontally right across the x or vertically right across the y. Okay. So something that's important here, you'll have to kind of think back and remember when we sample textures, oftentimes we're working in UV space, right? So 0 to 1. Here, we want to be able to look at individual pixels. So 0 to 1 isn't good enough because we have to offset by a pixel amount. So we need to actually know what the size of an image is, or a texture is, I should say. So we can use the OpenGL, or GLSL I should say, function texture size. So we're going to give it our image and 0, and this will return the resolution of our image. So in the case of our default crate, I think it's 512 by 512. Let's make sure we haven't broken anything. So this is actually kind of scaled out because of our aspect ratio being 16 by 9 when this is 1 by 1 aspect ratio. But this will give us that resolution. And I'm doing 1 over to invert it. We'll take a look at the math in just a second. So first off, I'm going to hold on to the result. Okay. So another thing we need to talk about, when I go back to this image, something you'll notice as well, this is a minor optimization, but something you'll notice is this array is symmetrical, right? So we have 7 values in this array, but this first value is the same as this last value. So what we can do to be even more efficient is instead of sending an array of 7 values, we can just send an array of 4 values. So we start here, this is index 0, index 1, index 2, index 3. And that's what we're going to do, just to ease passing our values. And you can see with Learn OpenGL's example, they just hard-coded in the shader. I actually wrote some code so we can auto-generate different kernel sizes, so we'll make use of that. But this is totally viable, and as we move forward, we'll start hard-coding it just for performance. And you can see here the largest value is that center pixel, because that should have the highest weight in our Gaussian distribution. It's the top of the bell. Okay, so that's why with our result here, we sample the pixel we are looking at. This is the middle pixel that we are actually evaluating, and we multiply it by weight 0 because that is that first maximal value. From there, this is going to be very similar to the OpenGL example, Learn OpenGL example. If horizontal is true, then we will loop through and we will add to our result texture, image, that text coordinate, So what are we doing here? We want to go 1 pixel over to the right. So what we're doing is we are sampling our texture, the same one. We use our starting coordinate, but we're adding to it I, which is going to be 1 for the first iteration, times that size. And so this is going to offset us just over by 1 pixel, which is why we involve texture size. Then we multiply it by our weight at I. Now this is moving in the positive direction because we also want to use go in the left side, the opposite direction, we'll do negative. And so with this symmetrical approach, we're going to fan out. If we had a hard-coded size like that Learn OpenGL example, instead of using a for loop, it would probably be a good idea just to say wait at 1, at 2, right? And just build it right in. Because we're going to make it dynamic so we can use different kernel sizes, we'll have it use a for loop. Okay, and pretty straightforward otherwise, we'll say else. So this means we're not going horizontally, so now we are going vertically instead. So our x value will be 0, and our y value will include the offset. Okay. At the very end, we will then return that result. Something that's important, I'm setting a transparency value of 1. Transparency usually doesn't come into this because we're just dealing with the colors, so I just set that to 1. Okay, so that looks good. We'll see if we have any issues. It's always go to compile and sometimes things come up. But we're good on the shader side. So on the CPU side, we need to load this shader. We need to set everything up properly to utilize this shader, and we're going to generate some, or make some code to generate our weights as well. Okay, that looks good. Now, let's see what we need to set up. Okay, so first off, I am going to add another function, which I'm just going to call simple blur texture. This goes back to my earlier point. Once again, I am using just one CPP file, and unfortunately C++ is not smart enough that if I have a function below my main, the only way it can know about it is if I define it beforehand. So this is not the implementation. I'm going to add it down below. This is just one of those annoying things about C++ being old school. We have to set it up before we use it. So I can do that, then at the bottom just do that. We're not ready to use it yet, but so this is going to be a function which takes in a input, which is going to be our texture we want blurred, and will return an output. So this is something that's important to keep in mind. If we wanted to lose our unedited image, we could blur it and overwrite this handle. But because we most likely don't want to do this, we want to keep our crate the way it was, we want to keep our matrix image the way it was, we're going to create a new texture and we're going to store the result in that new texture. That is important to keep in mind with these. If you want to blur, if every single update you're blurring an image, you could overwrite it, but typically this is what we want to do. Okay, so that looks good. The other thing we need to do, actually maybe we'll put it at the top. Let's add it up here. So the same thing, we're going to add a function I'm going to call calculate kernel, which will take in a size and create a kernel for us. Put that at the bottom. Okay. So to go along with that kernel, we're also going to make some variables to hold on to our kernel data. Kind of on the fence here. So when I did my example in my own kind of setup, I had 3 variables. So I made a kernel 2D, which is that full 2D grid. We don't actually ever use this. I don't even know if I use it in my code. Yeah, no. So maybe we'll get rid of this, seeing as it's just bloat, but I just wanted to have that to show. I have the kernel 1D, which is the full one dimension, and then I have kernel 1D efficient, which is that if kernel 1D is 7, their size of 7, kernel 1D efficient is 4. So we can pare it down just to 1, but that was kind of my thinking. Okay, so maybe we'll generate our kernel first, and then from there we'll start working on actually applying, because we're going to need a little bit of OpenGL magic to use our blur. Okay. So with calculating our kernel, I made use of this equation on Stack Overflow. I think someone did it with C++ here to generate our Gaussian values. We're going to take a look at the end of this at Intel's example. They have a little bit slicker code, but this is where I'm getting this from. I kind of mentioned you can adjust this sigma value to get different results out. We're just going to use this to generate varying kernel sizes. There is a little bit of difference you can get, but that's kind of where this is coming from. So this for loop will generate the kernel, and at the end we take the sum of it and we normalize it by the sum. The reason why we normalize a kernel like this is so in theory we won't adjust the intensity of the resulting image. So what I mean by that is all of these values, when we add all of the kernel values up together, it should equal 1, which means we're not adding any more color intensity or removing any color intensity, if that makes sense. Okay, so this is where I got this from. I just wanted to reference it. I always try to be sure to always include those. Okay, so I guess the other thing I need here is I need a kernel size. You know what, whatever. Okay, so if we're going to call this, we are going to clear our kernel 1D efficient. I should get rid of the M in front, shouldn't I? Because I didn't do that with anything else. Okay, so when we call clear on a vector, that just eliminates all the values in it. So the reason why I'm doing this is if you want to regenerate our kernel, I think I'm just going to make it so it happens at the very start of our code. But if you wanted to regenerate it mid-code or mid-execution, this will eliminate the values we had before. Most of what I'm going to do here, I'm just going to copy and paste because it is the same as that post. Okay, so we clear our kernel, we set that sigma to 1. We have this int w, we could really just use size instead. Maybe we'll do that just to be good programmers. Okay. You'll notice here I have this GLM pi. So I really like using GLM and I rely on it heavily. Part of the GLM library, GLM is a graphics math library which is used typically with OpenGL. So it has a header file you can include called constants. So what this does, that function, is we're saying to the GLM pi function, I want a value for pi and store it as a double. You can do this as an int, you can do this as a float. It's just depending on how much accuracy you want. So we'll add all those values together, then we'll use our sum to normalize them, and now we need to store the result in our 1D efficient. Okay, so at the end of this we will say funny, I started out using the range-based, and now I'm back to this. Okay. You can tell I wrote this one because I like to do plus plus rather than afterwards rather than beforehand. So what we're going to do with this kernel is we have this 2D value. To collapse it to 1D, we actually need to sum up in a direction. So we're going to go through and sum those values. So let's say float result is equal to 0 for int y is equal to 0, y less than size y plus plus. And we will say result plus equals kernel at x, y. Okay, so what's happening there if I go back to this guy? So I'm going to zoom in here. What you'll notice when you look at these values is none of these values directly match these values. So what's actually happened is to convert this from a 2D array of our kernel into a 1D, we go through and we add all of these columns together for the one-dimensional. So here we add all these together and we end up with 0.003. We add all these together. So we total all of them to create that 1D result, one-dimensional result. Okay. I could change my for loop here, but I'm going to be lazy. So we're going to say if x is equal or is greater than or equal to int size divided by 2, then kernel 1, oh, I got rid of the m, didn't I? Dot push back result. Okay, so what's happening here? We are only storing one side, right? So we want to store values 4, 5, 6, 7, if we have that 7. I don't know if I did those numbers right, but so we're saying if we are over the halfway point, then we store them. Okay. So that looks good. I'm going to make sure we call this right now before I forget, because I always forget to do these things. So in our main, when we go to set everything up, let's make sure we call that. So right after we load textures, let's call calculate kernel. And let's try 7 for now. It's important that it's a odd number as well, I should say, because it has to have the center pixel in the middle. All right, so that's going to provide us with the weight, and we can also use our dynamic array to determine the kernel size. We need to do a little bit of OpenGL work to make it so our outputted result can be captured. So, depending on if you've learn OpenGL's examples, if you've worked through that, you may know about frame buffers. So, a frame buffer is stored as a unsigned int, just like our textures, because we use OpenGL to create it. And a frame buffer is kind of a way to capture the outputted result of a render call. So we're going to use a frame buffer when we call this shader, and we're going to capture the resulting image from it. Okay, so this is our frame buffer variable, and I'm also going to create a blur working texture, which we can use to store that result. Okay. All right, that looks good. Let's also add a shader variable. Simple blur shader. I think I've changed this. I should go through and show you. So by default with Learn OpenGL's class here, this is your shader class. I just went in and I added a default constructor. If you don't have that, it won't let you make a variable like this. You have to create it immediately. The reason why I want to do this is I want to be able to use this shader across functions. Okay. And maybe the other thing I'll add here is I'm going to add a bool for blur dirty. So what I mean by blur dirty is this idea of a dirty bit. So if a change has happened, if we've decided to blur again, if we've changed our image, blur dirty is going to activate. The reason why this is important is these textures are differing resolutions. You at home may want to use different images. They can have different resolutions. So if we change our texture on the fly, we need to change the size of our working texture as well to capture that properly. So that's where that blur dirty comes in. Okay. So back down in handling our input, let's make sure we set that up as well. So every time we change our texture number, we're going to say blur dirty is equal to true. Okay. And in here, even when I swap these guys, I'm going to say blur dirty is true. Okay, that's good. Now, let's take a look into actually blurring our... Oh, wait. One more thing. Then we're going to get the actual magic going. We need to load that shader. So, like I said, we modified the shader class to allow us to create a shader variable and not immediately set a vertex and fragment shader. We need to make sure that we set it. Otherwise, it's not going to work for us. So that simple blur shader, I'm going to say, is equal to shader, and we're going to make the same call here. For me, I'm going to use that path to my desktop, and I believe I called them simple blur. The good thing with using Learn OpenGL setup here is there should be some error handling. It'll look to make sure that we have all this. Okay, happy with that. Okay, now we get to do the magic. All right, so I'm going to start out here similar to our other render call. I'm going to do a clear, set it to I'm not even sure if we really need to do a clear, but it is good practice. Sorry. Go. Okay, so we're going to do a check here, and we're going to say if our blur dirty is true. That means we need to recreate our textures. So this means a change has happened. So I'm going to see if output, so this is once again where we're storing our result, right? Does not equal 0. Then we're going to do GL delete textures. We're going to delete one texture, and we're going to give it our output. So what does this mean? I'm going to make sure every time I send a parameter in here, if I send a not created texture yet, I will set it equal to 0. So if output is not equal to 0, we're going to be resizing our texture. There might be a way to, without destroying the texture or deleting it, resize it. I'm just going to delete it here, then create a new one. If we skip this step, we're just going to keep using up more and more memory, and eventually we'll have an overflow. We're going to have an issue, a leak. Okay, and we're going to do the same thing with that blur working texture. Okay, let's make sure I set this to 0. Okay. So by doing that, then we're ready to say GL gen textures. We probably could just copy and paste this, but we'll go through it. So this is going to create our new texture, just like we did before. We're going to bind that texture. It is a GL texture 2D. Okay. I'm going to generate a texture with 4 channels. So I'm just going to use alpha no matter what. That's what I'm saying, in other words. Right, image 2D. You're going to use GL texture 2D. Number of components, 4. The size, I'm going to use textures at texture num to determine. We'll use m size dot x. Okay, so this is saying depending on what our currently selected texture is, we use that size. So again, we use RGBA, and we're going to do GL unsigned white. And the last thing, if we had any data to provide, we would provide it here. We're going to set it to null. This is going to be an empty texture because we're going to be capturing our output with it. Okay, so that creates our texture. I'm going to use the same hints we had above just because I don't feel like typing them out. So when we go up to that create texture, the wrapping and the filtering we will reuse. Okay, that looks good. What? I might just clamp to edge and do linear. Okay. And we're going to do the same thing with our blur working texture. Beautiful. Okay. So this creates our 2 textures. The other thing we're going to do here is we are going to bind our frame buffer. Okay. We have to say, sorry, GL frame buffer. Okay. And now we are going to specify our color attachment. So what does this mean? So this means our frame buffer is used to capture output from our render call, right? Texture 2D. Oops. GL frame buffer. Okay, so because our frame buffer is used for that, we are going to attach our texture and say for color attachment 0, right now there's only one color being outputted, so the only image result, we're going to capture it in blur working texture. Okay, so we're going to make sure that we attach that frame buffer when we do our render, and our resulting image, instead of being drawn on screen like we normally do, it's going to be stored in here. We can also make sure with this, if we have any issues with that attachment, we can throw an error, and I'm going to say blur dirty is equal to false. This is only going to happen when changes occur. We reallocate some things. Okay, so now let's actually get to our rendering. So I'm going to set our viewport to 0, 0. Then I'm going to use that same textures at num dot m size dot x. Okay, so what is this doing? Before we were doing our viewport for the size of our window. Here, because we are taking in a texture, blurring it, and outputting a same size resolution, we're going to set our viewport to match that. Okay. Excuse me. Now we're ready to kind of start setting stuff up. So I'm going to say GL active texture 0. I'm going to say GL bind texture. sorry. So we're going to take our inputted texture and bind that. We're going to bind our frame buffer. Now you might say, we just did that, why are we doing this again? The reason why we're doing this again is we only bind it when our blur dirty is true, right? So in case it's not true, we want to make sure we do it again. We're going to say blur shader, simple blur shader rather, use. We're going to set that kernel size. Oops. Dot set, oops, set float kernel size, and we're going to set it to our kernel efficient dot size. So this is with that vector function. This will give us the amount of items inside that vector. Now we're going to send an array out of the box with learn OpenGL setup. We have set float, set int, set bool. We don't have an option to set an array. What I did is I added in this one other accessor, which will give you the ID. So this is a GL uint, which represents the completed shader, which learn OpenGL has stored as ID. So it was private before. Oh wait, no, it is public. Oh, so I don't think I even need that. Never mind. So in that case, we can grab the location for weight. So we can say GL get uniform location. We'll give it the simple blur shader dot ID, and the uniform we are looking for here is weight. Okay, so we do that. So that's going to give us the actual location. Now we have to make sure that we actually set the value. So we're going to say GL uniform one float variable, which means it's an array of floats. This is the location we're setting. The number of items we are setting is the kernel 1D efficient, and the actual items we set, we say kernel 1D efficient at 0. Okay, just one. All right, so that means in here we have set our image, we've set our weight, we've set our kernel size, but we haven't set horizontal. Okay, so we'll say simple blur shader dot set bool horizontal to true. Okay. Something I'm going to do actually right now. So I have this blur working texture that I've created. I'm actually going to modify this. So right now, when we set our frame buffer, I'm going to set the output to this. So we're going to try just doing this once, doing a horizontal blur. We won't do horizontal then vertical, so we can hopefully ensure this is still working. To do our render, to make our lives easier, rather than setting up another VBO, doing the same vertex array call and everything, later on in Learn OpenGL, there's a function called render quad that gets introduced, which is just going to draw a quad for us on screen. We're going to make use of that here. Okay, let me just find it. Is it in here? Nope. Let me find that, sorry. Okay, so underneath here, you'll see this is a quad vertex attribute object, vertex buffer. It just says if it's set to 0 already, create everything, deer draw for you. Really, it's a little bit messy for us to be adding this in, but I'm just doing it to simplify things, to make our life a little bit easier. So we're almost there. Sorry, I know I just want to make sure I'm being careful. The last thing I'm going to do is when we're done here, let's set the frame buffer to 0. Okay, and with that, our simple blur texture should be good to go. So we're going to go back up to main in here. Before we do our render, before we draw our texture, we're going to check and see if blur is true. We'll do things a certain way, else we do our normal draw. Okay. Okay, so if blur is true, we are going to call blur texture, or simple blur texture. We're going to give it our textures at texture num.m handle. And we need to have a texture to output to. I know I made those working textures and everything. I'm going to create another variable here. There's probably a slicker way to do this, but just for simplicity, I'm going to do this. So I'm going to add in another output, so equals 0, and I'm going to pass that in here. Okay? So because we have that dirty check, output should be sized and created, no problem. And then the other thing we're going to do is if blur is true, then in here, instead of binding our full texture, we bind our output. If blur is false, we bind our output. Okay, let's try building this and let's see if I've forgotten anything. Oh, I don't know if I've set this as the starting project. What happens? No. Ah, geez. Of course. It doesn't like render quad because I didn't include up at the top. Okay. Now let's try that. Okay. So we have our normal functionality from before, rendering our normal textures. Let's see if I hit the B key if we notice a difference. Noticed a difference, all right, but something has gone wrong. Okay. So let's get to the bottom of this. First off, we know that the shaders aren't the issue because we didn't get an error. If there was an issue adding these shaders here, we would have gotten an error. So presumably we're going through. Let's pull up our shader here. Let me try just saying. Okay, so this is just setting that image. So if this is working properly, we'll just have the same image. I just want to make sure that our shader is running properly. No. Okay, so I've missed something along the way here. Good. Let's make sure I'm loading it properly. Right. I'm going to switch this to debug so I can make sure I hit this breakpoint, and I'm going to take a look. So if I hit B, the size looks good. Efficient looks good. ID is set properly. These are all positive signs. So, what's going wrong? This is always the fun part about doing these videos, is being like, how can things break live while I'm recording for me? Okay. Let's try this one more time. Let's go to the top. hit blur. Output is set to 0. Blur dirty is true. So we don't delete. Don't delete. Generate our texture. Right. Linear clamp to edge, which is good. Generate this guy, which we're not even using yet. Oh, I think I forgot to create our frame buffer. That would do it. I think that's what we're missing right now. So let's see. Okay, so up at the top of main when we get started, I made... Boo. So I made our frame buffer as a variable up above, but I didn't generate. We'll generate one. Okay. How does that look for us? Aha! Okay. Now let's switch this back. Sorry about that, but learning experience. There we go. Nice. Okay, so if I switch to release, we'll get better performance here. Okay, so with this, we can see we are blurring horizontally, right? You can see the minor bit of blur, and if we switch between images, you can barely even notice it with this one. And if we want to, in our render function, we can also set this to false and try it with our vertical. Okay. All right. So we have this working properly now. I guess something else we could even try as well. We'll see if we can see much of a difference. The Intel example is a little better for this, but varying the size of the kernel gives a different result. So you might look at this and say, this is not actually that blurred. Even if we're just working in one dimension, it's just a little squint, right? If we adjust this to a larger number, it should be a bit more blurred. So the larger the kernel, the bigger the impact we get with our blurs. Okay, so now we want to make sure that we blur horizontally and vertically. Now, the real pain in the butt thing with OpenGL is if we have a texture being bound as an input uniform, like our input texture here, to my knowledge, you cannot also store into that same result. Meaning, we need to have this kind of awkward procession where we're going to use this blur working texture. So we're going to render this once, store our horizontally blurred result in our blur working texture. Then we're going to change our frame buffer attachment here to be our output texture. We are going to set our input as the blur working texture, and then we do it again with horizontal to false. And now we get a fully blurred image. And we can switch around. Okay. So a little bit awkward here, and it's painful, the fact that we have to have this blur working texture, which we just use as that intermediary. With this, you kind of get a decent blur, but it's pretty minimal. As I said, we can adjust our kernel size. We could make it much, much bigger, and that'll have a bigger impact. I don't know, what can we try here? Let's try 31. The other thing we can do, we could use a small kernel, and we could actually run this repeatedly. So instead of just doing the one pass, or the one horizontal and the one vertical pass, instead we could run this multiple times, which I think we'll give a shot, and we might just do. Okay. So we could instead just make a temp variable. Temp is equal to input. Then we say for int I is equal to 0, I less than, let's do 5. So the reason why I made this temporary variable is the first time through, temp needs to be set to input. Then the last time through, temp needs to be set to output. And now we get a bigger result. If we want to, we can up this to something even higher. Let's try like 25. More and more blurred. Okay. So we're going to be looking at this in terms of performance. I might even fire up RenderDoc as I talk here. But something that's really important to keep in mind with this whole conversation is when it comes to blurs, like a lot of things with computer graphics, it kind of just depends on what you're looking for a result. So this is something where with your graphics application, with your game, you might want to adjust the kernel size. You might want to find just the right kernel size. You might want to use a small kernel size and repeatedly apply it, right? You might find you're over blurring it. You don't need that much blur. You would kind of tune it for the output result. So you can see here, we do drop our frame rate. I am still going 5 times, I believe. It might even, let me make sure I rebuilt it. Okay, so I'm doing this filter or this blur 5 times. You can see there is a noticeable impact on our frame rate. Not massively so. We lose about 200 frames, around that, maybe 300. It's hard to, obviously there's a lot of variability here. If we go to a higher resolution image, we'll see a bigger drop, and that's because there's more pixels to do this on. So hopefully this kind of sets the stage. Once again, I know I said this a lot with the text rendering optimization, but there's just so much variability when it comes to this stuff. Obviously you can see my FPS is bouncing around as it is, but then you get into what's the resolution of the image you're working on? What's the kernel size, right? All of these little things, even there's probably a little bit of work that could be done to optimize the shader a little bit better. So it gets very finicky, but hopefully we've laid down the groundwork now to see, okay, we have the blur working. Clearly, we get a decent result on screen. How can we make this more efficient? And this is right about where Learn OpenGL's code leaves off. They set this kernel, they hard-code it in, which would be a little bit faster, and that's kind of where they leave off. Our Intel article, however, keeps going, and it introduces a couple different concepts. So the first thing it introduces, which it sounds really silly, but is maybe not the first thing. The second thing it introduces, which sounds really silly, but is actually a really smart idea, is we can actually lower the resolution of our image. Obviously, if we do this, we're going to get a lower quality result. It goes without saying, right? If we half the resolution of our image, the quality is going to go down. We're going to lose quality. But if we're blurring things anyway, it's possible you might not even notice a difference. And when we run our blur algorithm on our halved image, that's half the number of pixels, right? So we could really save a lot of performance here. So that's going to be the next thing we work on. We're going to try adding a shader which will half our input texture. Okay, so up at the top here, I'm going to do a lot of the same things I did before. I'm going to add a function, half texture size. Just like before, it's going to take in a input, and it's going to return an output. I guess I don't even need to pass these by reference, seeing as we're just not, maybe I do actually. Okay, so this function is going to be responsible for that. What else do we need to add here? I guess I can create that. Okay, so we have frame buffer, our blurred texture. We're going to need a bunch of our logic similar to this. So instead of blur, this will be half pressed, and half dirty. The same way we need a texture to hold on to our results of our blur, we need a texture to hold on to our halved image, right? So I'm going to add in half shader. I could call it something better, but that should be good. I think that's about it. Okay, so now we need another shader, which is going to half the shader, the size of our texture, and then we're actually going to be able to use a lot of this code again. Obviously, we're going to remove all of the blur-related stuff, but we're still going to be creating a output texture to catch the results, and we're still going to be making sure that if there's changes, we apply them with the dirty bit. I might actually do that first. So in our process all inputs, we're now going to also add in, if we change our image, we are going to say half dirty is equal to true. Okay. And the other thing I'm going to add in here, so if we press the B key, we blur. If we press the H key, say half pressed is true. And we'll say half. Okay. Looks good. Okay, so now we have our logic. So if we press our H key, we'll be able to apply the shader. I am going to, on my desktop, once again, create 2 new files. So I might just call it half shader for our vertex and half shader for our fragment. It's important to note, I'm going to set this up to half our image resolution, right? You could as well have this be variable. Maybe you want to quarter it, maybe you want to go down by 1/6. Obviously, if we stick to powers of 2, we know things will be cleaner, but even still, it would be nice to have some variability in this, right? Okay, that looks good. So, I'm going to make that same change as before. So this is, once again, that texture shader that I've just duplicated. So I'm going to change this to coords. I just like that better because it's multiple coordinates. Okay, and we have a texture coming in. So this code I'm going to write is very heavily inspired, if not a copy and paste from the Intel example. They provide very good code with this. It helps quite a lot. Actually, you know what? With this setup, we don't even use this. We just take a position in. Okay. Get rid of text coords. And we say GL. Okay. That looks good. Now, in here, we have our sampler. We aren't using this. Okay, so if we sample here, this is going to grab the texture coordinate where we are currently looking. What we want to do instead, because we are halving, we want to take 4 pixels and we want to turn them into 1. So what we'll do is we'll sample 4 pixels, we'll take those values, average them, and store them as 1 pixel as our result. This one I might just copy. Okay, so we take the image size of our image, we're going to be halving it, and we use our GL frag coordinate. This comes through as part of the pipeline. We use this texture offset function, which is you pass the texture, change over. You pass the coordinate you'd like to sample at, and then you use this IVEC2 to offset, right? So we're moving over by 2. At the end, we add them all together, multiply by a quarter, and we store that value. And this is really in line with the Intel example. I guess maybe the code I have somewhere else. Okay. So that looks good. Sorry, I'm trying to pick up the pace now because I know I've taken a long time with that first step. Okay. Now, when we get to actually call this function, we're going to be able to reuse a lot of our setup as before. So in our half texture size, I might even just copy and paste the blur. We can work off of that. Okay. So we start off by clearing. We switch blur dirty to half dirty. We have our same output. We don't need to use this blur working texture anymore. Right. Okay, so we create our output texture if we need to recreate it, but the only difference here is we do size divided by 2 because we're going to half it. We can use the same frame buffer here. We don't need to recreate one. You noticed when I generated one, very little setup was actually done, so we can reuse that again. It's just used to capture frames. When we set our viewport, we set it to half the size. We're going to get rid of our loop here. So we send in our input. We bind our texture, or our frame buffer, which is good. We're going to use our half shader. Okay, and we will render the quad. Then set our frame buffer back to 0 to clear that. Okay, so really clean code here, not too bad. The only other thing we need to do, so obviously we need to add in the logic to call this, but because we now might be drawing half-size textures, when we go to blur our textures here, we're going to do a check and say if half is true, else. And we just need to split that in half, right? Because we do our half step before we do our blur step. So if we've halved our image, we need to make sure that our data that we're using to hold it, our texture we use to hold it, is halved. And we can do the same thing with our viewport. Okay, so if we're halving our texture, make sure that our whole blur pipeline is set up to use that half size. Okay, that looks good. Now, up above in our main, let's make some uglier branching code. So go to main. Okay, so right now we're saying if we blur, do this, otherwise do that. Now we are going to say if we blur and if half is true, else. Okay, so if we blur and half is true, we will send in our texture, and I'm going to make a new texture to hold on to the half output. So if blur is true and half is true, then we blur our texture. Did I call it? Or no, I called it half output. We do that, then, oh, whoops, sorry, I'm all over the place right now. Need to add in half. Half texture size. We store blur output. Okay. Then we send that into our blur here, and we store that as output. Okay? So otherwise, if it's false, we do what we normally do. Then if blur is not true and half is not true, we do our normal render. Otherwise, if blur is not true but half is true, then we will draw this. Okay. I think we should be good. Hopefully I didn't lose anyone there. I know I was going through. Okay. So if we hit half, you can see our resolution has gone down. Okay, so this is just doing half. And then if we do half and a blur, uh-oh. Somewhere my viewport is messed up, or my storage is messed up. I wonder in my keyboard handling, am I... Okay, they both get set to dirty, that's good. So... simple blur. If it's half, we do that. Oh, geez. Silly mistake. There we go. Have to get rid of that line. Okay. So you'll notice I can go to half, obviously a little bit more pixelated. When I blur, you don't notice the pixels at all with that lower resolution. This is with the half resolution, and blur. Okay. So something that's important when we look at this, if I pull up RenderDoc again, oops. Once again, as I was talking about earlier, halving these resolutions, it's all going to be variable, and it's all going to depend on what you're working with. So this texture is 512 by 512. That's not a very large image. That's not that many pixels to do a blur on. So when we blur, we're losing maybe 200, maybe 300 frames, right? If I go half, you notice we drop, I don't know, 50 or 60 frames, maybe a little more. And then when we blur, it's almost, it looks like it's less performant than before, right? So we're almost better off just blurring. But if we switch to a higher resolution image like this screenshot and we blur, sorry, 1 second. Let's try that again. Our frame rate is impacted heavily, right? So without the blur, 360. With the blur, almost halved, over halved. But if we go half resolution, we gain performance back because it all depends on, is it worth the cost of halving our texture? With a 512 by 512 texture, that's a decently expensive operation to half the texture. It might not actually pay off. With something like this, where it's HD resolution, halving it, although it's expensive, it's then worthwhile for when we go to do our blur. The other thing I'll draw attention to is when we half it, the blur is actually kind of increased. It makes it more severely blurred. So this goes back to my earlier point of these are not cut and dry techniques. These are not things where you're just going to say, okay, I always use this kernel size, I always half the resolution, I always quarter the resolution. These are things that you want to be able to adjust. So even if you're not interested in writing OpenGL code, if you want to use like Unity or Unreal, these are important things to understand because you can use their pipelines and adjust them to fit your needs well. Okay, so our very last little trick we're going to talk about. The Intel article has one more trick, but the one we're going to cover last here is, right now, we sample every pixel individually and we apply our kernel, right? Well, there's actually something we can do to speed things up even more. And we've seen this before if you've done any OpenGL development. And we've actually been setting the way this works each time. We've been setting our parameter for our filtering to linear. What this means is if we have a UV coordinate that's in between 2 pixels, do a linear blend, a lerp, between those 2 colors. And that can all be done on hardware, and GPUs are built to do this. So what this means for our blur is we can actually cut down on the number of samples by using pixel coordinates that are in between full pixels. So where before we had these 7 pixels we would sample, we can cut that down to 4 by using these locations that are in between 2 pixels. Now this adjusts the weights that we use because we're not going to be able to use the same values as before, but it means we go from 7 samples to 4, which makes a huge difference. And you can imagine as we get larger and larger images, this can really pay off greatly. Plus, our hardware is already ready to do this. Our hardware, our GPUs, are used to sampling textures like this. So we can make use of this and really speed up performance. You can see with the provided code they have here, they have a kernel width of 7 by 7. We only use 2 steps because you have to remember it's symmetrical, right? So we sample these 2, that's 1, then these 2, that's 2. They have our weights and our offsets. Okay, so we're going to give this a shot and we're going to compare the performance of this. I'm going to go over once again. I'm going to duplicate those shaders. I'm going to call this fast blur, which is really nondescript and you probably shouldn't call it, but okay. Let me merge this with my other ones. Okay. So this is the same setup as before. We're now going to set this up to use this new improved lerp setup, I guess I would say. Okay. So once again, I'm actually going to modify this. We don't need to be taking in these vec2 or vec3s. I really should have done that with the other one too. But so we have our texture coordinate. That's good. We're going to set this. Okay. I guess I'll call it the text coordinate like they have. Okay, this is another trick you can use. Instead of actually sending UV coordinates, you can just use your position to determine that. I think we did that with our text improvements. Okay, and so now we end up with a kind of similar approach to what we've done in the past with our simple blur, right? With our loop, we figure out the size and we set things up. So to go along with this, we have our texture we're going to sample. We have a bool for horizontal or not. We have our vtext coord in, and we have our frag color out. Okay, so I'm going to determine our size here. Right, so just like before, we're going to determine our texture size. We use this with our setup here. Right now, this is going to have the horizontal resolution, the vertical resolution. I'm going to set those to 0, depending on if horizontal is true or not. And I'm actually going to use a separate function for our Gaussian blur. So I'm going to add here this function. It takes in the image we want to sample, it takes in our center UV, and it takes in our pixel offset. Okay, you're going to see kind of why I'm starting to try and make this more modular. Okay, so we're going to say frag color dot RGB is equal to Gaussian blur, and we give it that texture, we give it our coordinates, and we give it our size, and then I'm just going to set the alpha to 1. Okay. Now, what's really cool I've gone through that Intel example code that they provide. It'll auto-generate different weights and offsets for you. So I've gone through and I've just set those up. I'm going to grab those and place them at the top here. So I've created it so you can just go through and say G weights 2, G weights 2, G weights 4, offsets 4. And you can just select them. Obviously, it's not the cleanest thing ever. This is kind of goes to what I was saying earlier. You might want to go through and adjust and check to see is it blurred enough? Do I need to blur more? Do I need to blur less, right? But if you want to adjust, if you want to lower the number, just go in here, change that, and we change that. You could do an array of arrays as well if you wanted to make things a little slicker, but okay. So that looks good. At this point, the amount of work we need to bring this in is pretty minimal because it's mostly going to be the exact same setup as what we've been doing. So I'm going to add in another function. This time, we'll call it our fast blur. Okay. The bottom here. Add that. Okay. Now, of course, we need to add in some more button handling. So we'll say fast blur. Okay, we add all of those. We'll add in a fast blur shader. And I think with that, we should be pretty good. We're going to go in, and now we're going to load that new shader. Okay. Now, with our keyboard handling, we got to make sure that we set all of these. Okay. So, say fast blur dirty. Let's go to true. Okay. And I'm going to say if you press the F key for fast, then we will say fast blur pressed. Okay, now the other part of this is with our half shader, we can half and then blur, right? Where what we're going to do now is we're going to make this mutually exclusive. So if we are doing a regular blur, then our efficient blur, our fast blur, is disabled. Oops. Same thing, if we are doing a fast blur, then blur is disabled. You can only do one blur is what we're saying, because otherwise we'll just get messy results. Okay. So now we go down. I'm going to once again copy the simple blur. Right. We paste that. Okay, so if fast blur, oops, is, oh, I lost it, sorry about that. If fast blur is dirty, we do that. I'm going to use the same working texture. The reason for this is, once again, we can only do one blur at a time. I've set that rule. Okay, so I'm going to use most of the same setup here because we can. Everything else looks good in here. We still bind our texture. We still set horizontal to true. We no longer need to set our sizes because we have those predefined weights and offsets. Okay. That looks good. Okay, now we have to go back up to main and deal with that rat's nest of if statements. What we're going to do though is, so right now we have this check to see if our blur is true. We're going to do similar, and we're going to say if our fast blur is true. So if fast blur is true, then we do fast. What did I call it? Oh, I called it fast blur size, jeez. Sorry. Should be fast blur texture. There we go. Okay. So, if fast blur is true, do the same stuff, but now we're saying fast blur texture. Else, if half is not true, do this. Okay. And we should be good. Let's give this a shot. Okay, so if we do a blur, uh-oh. Make sure I didn't mess up my keyboard handling. Right. This looks okay. Why did nothing happen when I... The fact that it's toggling like that, I think I might have messed something up. Oh. There we go. That would make more sense. Okay, so our half is working. Our blur doesn't seem to be working. The frustrating thing is this is not even, I just want to make sure this works, but this isn't even like the actual logic, it's just, okay, blur is equal to true. Right. Now let's go to our simple blur texture. Okay, that looks good. I wonder, did I remember to change the dirty on this guy? Should be fast blur dirty. Okay, let's try that. Fast is working. Half is working. But the regular is not. So I've done something wrong in here. Okay. Oh, this needs to be else if. Gosh, sorry. I feel like doing these code-along videos at this length. I just stop. I start making dumb mistakes. Okay. I think we should be good. So let's switch over to our release. We'll do a build. Okay. Now we open up render doc and we'll take a look. Okay. So let's go with our most intensive one. If we blur our screenshot, we lose about half. If we do a fast blur, why is that having such an impact? Oh, you know what? I think the issue is this needs to be 2 to do an apples to apples comparison, right? So it's should be using 2 samples instead of using 4. Otherwise we're using twice the kernel size, which is not a fair comparison. Okay, so blur on this guy, 1500 about. With our fast blur, about 22, 21. And if we half that, pretty close to normal. We switch over to our normal blur, a little bit of a difference. So you can see we are getting a performance benefit, and it all is going to depend on how large our image is. Okay. I think now's a good time to pull up the actual project that Intel website gives you, because it is quite cool and it lets you compare these apples to apples. So I'm going to pull up fast blurs. Okay. And is this going to bug everything out? Oh, jeez. Sorry. Upgrading to the newest Visual Studio has broken some things. Let's try that. Cool. So this is Intel's kind of test platform that they give you. What's really cool with their code is, so I copied over these arrays, right? What's common in advanced graphics is you'll write C++ code that creates strings that'll recompile as shaders. You see it a lot, actually. Lots of Unreal 4 games and some 5 games, you'll get frame rate hitches from the shaders being recompiled. So this will actually do that. And what's really cool is if I double click, it actually will give you the shader that they've created and let you copy it. Okay, so they give you a couple different scenes you can take a look at. This is with the blur off, obviously. We'll do a high resolution here. We can look at the downsample. Pretty minimal difference. Wonder. There you go. Now you can kind of notice the difference. If we do a Gaussian blur, and you can see we are blurring with 35 by 35 if we go down to 7. So this is really nice because we can get a look at how much these kernel sizes actually impact things, right? Now, if we, so this is doing it with a full resolution with those kernels. So if we do a 7 by 7 with a full resolution, if we go to half, go to a quarter. So it's really interesting to be able to take a look at this and see what a difference we get. Like, look at it with this huge kernel and with a quarter resolution, everything just becomes non-distinct, right? And you can check out this graph, which is pretty neat. We didn't cover it. They cover another blur as well. 2 other blurs, really. But it's very neat to be able to check out these different comparisons, apples to apples. Doing the code the way we did it today, using Learn OpenGL as the starting point. The only downside is, you know, I don't want to go in and add ImGUI or add in UI elements to be able to toggle things like this, but super, super cool to be able to compare them. So let's kind of polish this off here. So with today's video, I wanted to take a deeper dive into blurs and see kind of how we can optimize them and some of the interesting ways that we can improve the performance as well as what they're used for. This Intel article, like I said, I would highly recommend taking a look at. There's more advanced filters they also have in here, and you can also download the application I showed you and you can try it on your own machine. I'm going to post all of my code I created today on GitHub. If you have any issues, if you have any questions, send me a message on there, report some issues, and we'll polish it up together. Otherwise, hopefully you guys enjoyed this. Like I said in my other video, I've been thinking a lot about other OpenGL projects we could do together. I know the text rendering was one where I kind of came up with everything on top of the OpenGL solution. This one's more of an examination of some code that everyone has access to. Maybe next time we can make something together again. Anyway, have a great day. I hope you guys enjoyed it. Be sure to like, comment, and subscribe. Bye, everyone.